Welcome back to Digital Systems 1. In today's video, we are going to discuss digital arithmetic. When I use the word arithmetic, I'm specifically talking about addition, subtraction, and multiplication. You already know how to perform these functions using a decimal number system, but today we're going to learn how to do this all in binary. We're also going to learn how to represent negative numbers, also called signed numbers, and be able to perform addition and subtraction using both positive and negative numbers. So before I discuss binary addition, let's review how we normally would perform addition using decimal numbers. If you go all the way back to 3rd or 4th grade, you learned about the place value system. So you learned about the ones place, the tens place, the hundreds place, and so on. And when we add two numbers together, we basically start with the ones place. We add 6 plus 1 to get 7. Then we add 7 plus 6, which equals 13, which means I need a carry. So I'm going to take the number 13, I'm going to write the ones digit of 13 down below, and the tens digit goes right here. So we have a carry of 1. Then I perform the last addition by saying 3 plus 4 plus 1 to give me 8. That same idea is going to apply to binary addition, except we don't have the decimal number system anymore. We don't have a base 10 system, we have a base 2 system. So it's going to be slightly different, but for the most part, you're going to think about the process the same way you would normally add numbers. So here are some examples. Starting on the left with number 1, we're going to add the number 011 to the number 110. These are binary numbers, so we're going to add in binary. So we're going to begin on the left and we're going to add 1 plus 0. And we know that 1 plus 0 equals 1. Next, we're going to go to the middle column here and we're going to add 1 plus 1. Now, we know that 1 plus 1 is 2 in decimal, but 1 plus 1 is 10 in binary. 1 plus 1 is 10 in binary. And so now when we look at that 10 as a result of adding 1 plus 1, we have a sum and a carry, just like you have a sum and a carry in decimal addition. The sum is going to be written below the column you're adding. The carry will be carried forward to the next column. So when we add the number 1 plus 1, we get a sum of 0 and a carry of 1. So we would say that 1 plus 1 is 0, carry the 1. And again, that 10 is the result of adding 1 plus 1 together. So for the third column right here, we're going to do the carry 1 plus 0 plus 1. So essentially we end up with the same condition here where we have 1 plus 1. So you're going to have 1 plus 1 equals 10. You're going to write the sum below, so the 0 is going to go right there. And then since we don't have any other numbers to add, your final carry goes right down below. So we can see that 011 plus 110 is going to give you a final answer of 1001. Since we know how to convert all of these numbers back to decimal, the best thing to do now is to check your work by doing exactly that. 011 is 3 in decimal. 110 is 6 in decimal. We know that 3 plus 6 should equal 9, and 1001 is in fact 9. So we can check our work every single time by converting everything to decimal and doing the addition as you normally would to make sure that your answers are correct. Let's look at example number 2. We're going to start on the right and work our way to the left. So 1 plus 1 is going to give me a 0, carry the 1. Referring back to this example here, we get 1 plus 1 is a 0, carry the 1. Next, we have 1 plus 0 plus 1. So essentially that's 1 plus 1 again. So we have 0, carry the 1. And then we have 1 plus 0 plus 1 again. So that's essentially 1 plus 1. 1 plus 1 is going to give me a 0, carry the 1. And then at the last column, we now have a carry plus 2 additional 1s. We have 1 plus 1 plus 1. Well, we know in decimal, 1 plus 1 plus 1 would be 3. In binary, 1 plus 1 plus 1 would be 1, 1. 1, 1. So the sum and the carry for this operation are going to be both 1, we have a carry of 1 and a sum of 1. So we would say that 1 plus 1 plus 1 is equal to 1 carry the 1. And in this case, we don't have any other numbers to add. We're in our very last column. So we're going to write the sum and then the carry right out front. And that's how we would add 1 plus 1 plus 1. If you're having trouble doing these conversions in your head, you will want to stop and review the very first lecture of the semester, which discusses how to convert between binary and decimal. By now, this should be very comfortable to you. And looking at something like 1, 1, you should pretty much automatically know that's 3, or at least remember the process for how we got that. So if you're feeling a little foggy on these conversions, you will want to stop this video and review converting from binary to decimal, because that's the only way you're going to really understand if your work is right, is being able to understand those conversions. I'm not going to review how to convert from binary to decimal in this video. By now, that should be something that you're familiar with. So let's continue with example number 3. It's a little bit longer. You have two 8-bit numbers, but the process is going to remain the same. We're going to start from the right, work our way to the left, and add up each column. 1 plus 0 is, let me back up and check our work right here. So for this problem number 2, 1, 0, 0, 1 is a 9. 1, 1, 1 is 15. So 9 plus 15 should equal 24. And if you convert 1, 1, 0, 0, 0 back to decimal, you will see that that is 16 plus 8, which is 24. Now on to our third example. We're going to start from the right, work our way to the left, and add up each column. 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 is 0, carry the 1. 1 plus 1 plus 0, that's 1 plus 1. 1 plus 1 is 2. Remember, 2 in binary is 1, 0. So we have 0, carry the 1. Same thing here. We have 1 plus 1 plus 0, which would give me 0, carry the 1. Here I have 1 plus 0 plus 1, which again will give me 0, carry the 1. And finally, 1 plus 1 plus 0 is again 0, with the final carry of 1 being written out front. That's how we would do problem number 3. And let's look at problem number 4. So we have 1 plus 1 would be 0, carry the 1. And right here we have 1 plus 1 plus 1. That would be 3. In binary, that's a carry of 1 and a sum of 1. So we have 1, carry the 1. 1 plus 0 plus 0 is 1. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 right here is 0, carry the 1. 1 plus 0 plus 0 is 1. And then 1 plus 1 is 0, carry the 1. So this is how we do binary addition. Again, you're always going to want to go back, convert your answers to decimal, and check your work. So for numbers 3 and 4, I'll leave that up to you. Next, let's go over subtraction. And subtraction of two binary numbers is performed the exact same way that we subtract decimal numbers. And let's review that as well. So if we were going to subtract these two decimal numbers shown here, 687 minus 492, we would start with the ones place and we'd say 7 minus 2 is 5. Then we'd get to the middle column and have 8 minus 9, which we can't do without a borrow. So we'd come over here, we'd cross out the 6, we'd make it a 5, and then the 8 would become 18. And then we do 18 minus 9 to get 9, and then we do 5 minus 4 to get 1. Same idea in binary. We're going to be borrowing from a neighbor if we can't perform the subtraction as shown. And when borrowing in binary, the column that provides the borrow decreases by 1. So if you're borrowing from a column that has a 1, that 1 will become a 0. If you're borrowing from a column that currently has a 1, 0, it will become a 0, 1. Remember, this is 2 in binary. 2 minus 1 is 1. This is 1 in binary. And if you're borrowing from a column that has a 1, 1, that's 3. 3 minus 1 would be 2. 2 is 1, 0 in binary. The column that receives the borrow goes from a 0 to a 1, 0. Now again, that's 1, 0 in binary. So the column that receives the borrow is not equal to 10. It's equal to 1, 0 in binary, which is 2. 2, not 10. So let's look at some examples. So in this first example, we have 1, 1, 0 minus 0, 1, 0. So we're going to start from the right and work our way to the left. So we're going to start with 0 minus 0, which is 0. There it goes. 0 minus 0 is 0. Next, we're going to do 1 minus 1, which is also 0. Then finally, we're going to do 1 minus 0. 1 minus 0 would be 1. So in this case, we didn't need to borrow at all. And if we check our work by converting to decimal, 110 is 6. 010 is 2. 6 minus 2 should equal 4. And that is correct because we have 100, which is 4 in binary. Now let's look at an example where we're going to have to borrow. Again, we're going to start from the right for the example number 2, move to the left. 1 minus 1 is 0. 1 minus 0 is 1. 0 minus 1, here's the subtraction we can't do. We can't do 0 minus 1. We need the top number to be larger or equal to the bottom number. So here's where we're going to borrow. So we're going to go to the next column over and borrow from right here. So this 1 is going to be crossed out, and it goes down by 1. So that 1 is going to become a 0. And then the column that receives the borrow is going to go from being a 0 to a 1, 0. Remember, this is 2, not 10. So now this value is 1, 0, which is 2 minus 1. 2 minus 1 is 1. Then we get to this column here and we have 0 minus 1 again, which means we have to borrow again. So we're going to go to the next column over, cross it out, decrease it by 1, so this column will now be 0. And then the column that receives the borrow goes from 0 to 1, 0. So now we have 1, 0, which is 2. 2 minus 1 is 1. And then we have 0 minus 0, which is 0. So if we convert this to decimal to check our work, 11011 is 27. 01101 is 13. 27 minus 13 should be 14, and that's what we have right here. 01110 would be 8 plus 4 plus 2, which is 14. Let's go to example number 3. We're going to start with 1 minus 1, which is 0. Then we have 0 minus 0, which is 0. 0 minus 0, which is 0. 1 minus 0, which is 1. And then right here, we have 0 minus 1, which we can't do. If we go to our neighbor has nothing to provide for the borrow. So this is an example where you would have to do a double borrow. So this neighbor is going to have to borrow a 1 from here, making that column 0. So now this column right here is now going to become a 1, 0, which is 2. So now this neighbor has 2. I can now borrow from that neighbor. So I'm going to cross out the 2. So the 1, 0 decreases by 1. 2 minus 1 is 1. So now this becomes a 1. So that the first 0 right here can have the borrow. This 0 right here will receive the borrow and become a 1, 0. That's called a double borrow. So now we have that this column has become 2. 2 minus 1 is 1. This column borrowed and became a 2, but then it gave away one of its 2, so now it only has 1. 1 minus 1 is 0. 0 minus 0 is 0, and then we have 1 minus 0 is 1. And there's our final answer for that subtraction. So keep in mind that you may have to do a double borrow if you go to borrow from a neighbor and the neighbor has nothing to provide. Look at example number 4. 1 minus 0 is 1. 1 minus 0 is 1. 0 minus 1 we can't do, so we'll have to borrow from right here. So I'm going to cross out that 1 and make it a 0. And then this 0 becomes a 1, 0. 1, 0 is 2. 2 minus 1 is 1. 0 minus 0 is 0. 0 minus 0 is 0. 1 minus 1 is 0. 1 minus 0 is 1. And 1 minus 1 is 0. And that is how we perform binary subtraction using the borrow method. Next, we're going to talk about signed numbers. And by signed numbers, we mean negative numbers. In binary, there are 2 ways to represent signed numbers. The first way is to add a signed bit. And a signed bit is a bit that goes on the beginning of the number. If the number is meant to be interpreted as a positive number, the signed bit will be 0. If the number is meant to be interpreted as a negative number, the signed bit will be 1. And here's an example. Let's say we're going to represent the number negative 17 using a signed bit. Use 5 bits to represent the number and 1 bit for the signed bit. Keep in mind that as we represent numbers, especially signed numbers, you'll be given a description of how many bits to use for the number, and then you'll add a signed bit to that quantity. So you're always going to want to make sure you follow the directions provided and know how many bits you have to represent the number. So the number negative 17, we have 5 bits to represent that number. So what we're going to do is we're going to start by just writing out the number 17 in binary and making sure that we use 5 bits to do it exactly. So the number 17 would be 16 plus 1, giving us 10001 as our representation of 17. So then to represent negative 17, we're just going to add a signed bit in front of that binary representation. So we have the 1001 representing the number 17, and then a signed bit in front telling me that that number should be negative. So we call this a signed binary number. With signed binary numbers, the most significant bit has no value. So this doesn't actually represent a place value. It just represents a plus sign or a minus sign. That's it. So when you're dealing with a signed number, you'll never assign a place value to the first bit. The first bit will only tell you whether the number following that is positive or negative. So let's do some examples. We're going to convert the following numbers to signed numbers using 4 bits to represent the number and a 5th bit to represent the signed bit. So if you have the number negative 10 in decimal, you're going to write out negative 10 in binary. You're going to write out just the number 10 in binary first. The number 10 would be 1010. Then to make it a negative 10, add a bit in front. Add a 1 in front for a negative number. With negative 14, you're going to write out that number in binary, which would be 1110. Again, we're using 4 bits to represent the number based on the description above. Then we're going to add a signed bit to the front of the number to represent negative 14. With the number 4, the 4 here is positive. So we're going to write out the number 4 using exactly 4 bits. 0100, and then we're going to add a signed bit in front to that 4. We're going to add a 0 in front. So the first bit tells me that it's a positive number, and then the 4 bits following tell me the magnitude of the number. Next, we're going to talk about how to represent signed numbers using a different system called the 2's complement system. The 2's complement system was created as an alternate to using a signed bit in order to represent a negative number. And there are a few steps that we're going to take to use the 2's complement system. So to convert a negative decimal number to the 2's complement system, here are the steps. First, you have to complement the binary value of the number. And complement just means invert. Every 0 becomes a 1, every 1 becomes a 0. Then you're going to add 1 to that number you've complemented. And by adding 1, I literally mean you're going to use the addition process we discussed earlier to add 1 to that number. And then you'll add a signed bit of a 1 in front. So let's go through an example where we're going to represent the number -17 in the 2's complement system. We're going to use 5 bits to represent the number and 1 bit for the sign bit. So we're going to start by taking the number 17 and writing that in binary using exactly 5 bits. The number 17 would be 10001. Next, we're going to complement that number, which means every 1 will become a 0 and every 0 will become a 1. The complemented number would be right here, 0110. Next, we're going to add 1 to this number. So you're literally going to take the number you've complemented and add 1 to the far right column. And if you have carries, you will include those carries just like we've shown previously. So in this case, we have 0 plus 1 is 1, and then we have nothing else here to add. These are all considered to be 0 here. So we have 0 plus 1 is 1, and then 1 plus nothing is 1, 1 plus nothing is 1, 1 plus nothing is 1, 0 plus nothing is 0. So now we've complemented the number and we've added 1 to get the number 0111. Lastly, we're just going to add a sign bit to the front of the number. So in the 2's complement system, -17 is represented as 101111. Here's the most important thing to remember about the 2's complement system. In the 2's complement system, the most significant bit has a value and is also negative. All other bits are positive. So in order to check that your answer is right in the 2's complement system, you will assign a value or a weight or a place value to the first bit, but also make it negative. So if I were to convert this number to decimal, I would look at this and say that this is 2 to the 5th, 2 to the 4th, 2 to the 3rd, 2 to the 2nd, 2 to the 1st, 2 to the 0 power. That's all true, except this first bit is now going to be a negative value. So the first bit is going to represent -32. We have nothing for the second bit. We have 8 plus 4 plus 2 plus 1 for the last 4 bits. Now, if you go to your calculator or if you add this up by hand, you'll see that -32 plus 0 plus 8 plus 4 plus 2 plus 1 is equal to -17. So when you convert a number into the 2's complement system, this is how you'll check your work to make sure that you converted it properly. If you assign a weight and a value to the most significant bit, and then positive values to all the other bits, and add it up, you should get what you started with, which was, in this case, -17. So here are some examples where we're going to convert these numbers to 2's complement numbers. We're going to use 4 bits to represent the number and a 5th bit to represent the sign bit, and check our work when we're finished by using that idea that the first bit has a negative value. We're going to start with the number -10. And we're going to use the same example as before, simply to illustrate that 2's complement numbers and sign numbers don't look alike. So when we compare this answer to the answer in the previous example, we'll see that if you are converting to the sign number system, your answer is going to look different than the 2's complement number system. So we're going to follow the steps, beginning by converting the number 10 to binary, using 4 bits. That would be 1010. Next, we're going to complement, which would be to make every 1 a 0 and every 0 a 1. That would give you 0101. Next, we're going to add 1 and a sign bit. So, if we take the number 0101 and we add 1 to that number, you'll get the number 0110. Again, I'm not going to show that process, but you should take a second to pause the video and verify that this is true. And once we get this number 0110, we're then going to add the sign bit right in front. So our answer ends up becoming -10 in base 10 is equal to 10110 in the 2's complement system. Notice I use the subscript of 2C so that I know that this number is in that system. This is how we'll tell the difference between various systems. So the subscript 2C will always represent a 2's complement number. Next, check your work. Remember, the first bit has a weight and it's also negative. So we have -16 plus 0 plus 4 plus 2 plus 0 adds up to -10, which is what we started with. As long as you end up with what you started with, you know that your number is being represented correctly for this system. Let's do another example. This time we'll do -14. We're going to follow the same steps as before. Convert the number 14 to binary using exactly 4 bits per the directions. Remember, the directions tell you how many bits to use to represent the number. So we're going to take the number 14, represent that using 4 bits, which would be 1110. Complement the number so that it becomes 0001. Add 1 as well as your sign bit. 0001 plus 1 will give you 0010. That's basically 1 plus 2. Then we add the sign bit in front, right here. So our answer is that -14 in the decimal system is equal to 10010 in the 2's complement system. And then we'll check our work. So we'll have -16 for the first bit, plus nothing, plus nothing, plus 2, plus nothing. -16 plus 2 is equal to -14. So we know our answer is correct. Lastly, we'll do -4 this time because the 2's complement system is only for negative numbers. You don't need it for a positive number. So we don't need to convert a positive number into the system. So we'll do -4 for this example. Same process as before. Convert to binary using 4 bits. The number 4 would be 0100. Complement that number, 1011. Add 1 and the sign bit. 1011 plus 1 would be 1100, and then a sign bit in front. So -4 in the 2's complement system would be 11100, and here's our check to make sure that that's true. If you're looking at my check, you actually should see a small mistake here. These numbers should not have a negative sign in front of them. So I'm going to cross those out. These should just be positive numbers. Sorry for that mistake. So your answer here is -16 plus 8 plus 4, which is equal to -4. Now that we've talked about sign numbers and 2's complement numbers, here's a small exercise to make sure that you have both systems straight in your head. So you have a table, and you're going to represent the following numbers as both a signed number, remember that's just adding a sign bit, and as a 2's complement number by converting the number using the process we just discussed. You're going to use 4 bits to represent the number and 1 bit for the sign bit. Remember, positive numbers are represented the same way in every system, so we only need conversions for negative numbers. And you have 3 examples shown in this table. So what I'd like you to do is take a second, pause the video, and try to do these on your own. Make sure you understand the steps for both systems. So take a second, hit pause, and when you're ready, hit play to see the solutions. And here are the solutions for each number. -11 in signed binary would be 11011. And notice that I use a subscript of 2s to indicate signed binary. It's a base 2 number that's a signed number. And then we have 2c as our subscript for the 2's complement numbers. Take a second and check your work. If you did not get these answers shown on the screen, try to go back and figure out where your error might have been and review the steps we discussed in the past few slides to make sure that you're following the process correctly. Now we're going to kick it up a notch. On the next page in your notes, you have a new table. You have 3 columns, decimal, signed binary, and 2's complement. And now you're going to go in between all 3 systems. So for the first row, you have a 2's complement number given to you. And you're going to determine what that 2's complement number would be in decimal and in signed binary. You also have a signed binary number given to you in the middle section right here. You're going to want to convert that to decimal and then to 2's complement. And then you have a decimal number right here that you have to convert to signed binary and 2's complement. So again, what I'd like you to do is hit pause and attempt to figure this out on your own. Remember, watching me do it isn't really learning. You've got to eventually apply it yourself. So hit pause and try to complete this table on your own. When you're ready, check back in for the answers. All right. And here are the solutions one by one. With the first row, the easiest way to approach this is to take that 2's complement number and figure out what it is in decimal. Remember, the first bit has a weight and it's negative. The first bit would be worth 2 to the 7th, and it also would be negative. So 2 to the 7th is negative 128, plus 64, plus 16, plus 8, plus 4, plus 2, if I add up all the other place values where there's a 1. And you get the answer negative 34. So this number in 2's complement is equal to negative 34 in decimal. Now that I have that, I can convert that to signed binary by writing the number 34 in binary using 7 bits for that number, and then adding a 1 for a signed bit. Here's what that would look like. So notice the 2's complement and signed binary versions look very, very different. You're not going to get the same values for these different conversions. Next, you have a signed binary number given to you right here. Remember, with a signed binary number, the first bit is the signed bit, and then following that is the number that is being represented. The first bit here is 0. That means that this number is positive. Then you're going to figure out the value of the number by taking the following 7 bits and converting those 7 bits to decimal. That would give you 64 plus 32 plus 8 plus 4 plus 1, which is 109. And now you have to write this same number in the 2's complement system. Well, remember that a positive number doesn't need any conversion at all. It's going to be the same number in binary, signed binary, and 2's complement. There is no conversion process required for a positive number, only negative numbers. So the 2's complement would look exactly the same as signed binary. There's no conversion necessary for a positive number. And then we have negative 115. And you can choose where you want to go first with this, whether you want to convert to signed binary or 2's complement. If you decide to go to signed binary first, you'll see that the value for 115 in binary is 1110011, and then your signed bit goes right in front. With the 2's complement, you have to write out the number 15, complement, add 1, and you'll end up with this answer right here. So that's the answer to the table. Make sure that you can do these types of conversions on your own. And if you're having any questions, feel free to reach out to me so that I can clarify that further. Next, we're going to add in a little topic here called sign extension. Let's say that you want to store an 8-bit number into a 12-bit space. When you think about memory, memory can store groups of bits, and memory has different types of sizes and structures. So you may have an 8-bit number that can fit into a 12-bit space inside of a memory system. And to preserve the value of the number, you have to perform what's called sign extension, which means we have to extend that 8-bit number so that there are 12 bits. But we don't want to change the value of the number by adding more bits to the number. To perform sign extension, you add leading zeros for a positive number and leading ones for a negative number. That just means you add zeros or ones to the front of the number based off of what the first digit is already. So using the previous example, we're going to sign extend each answer in the 2's complement column to fill a space of 12 bits. So in the last example, we had in the first 2's complement answer was 1101, 1110. If we're going to sign extend that, we're going to look at the first bit. The first bit is a 1. And then we're going to add extra ones in the front of the number to fill the space required. In this case, we need 4 extra bits. They're all going to be 1s to sign extend that number. If you have a positive number like number 2, the sign extension would be all zeros because the first digit is also a 0. And then with number 3, to sign extend that number, you would again put 1s in the front of the number. And by doing this, we can create a number that is longer in terms of number of bits, but we haven't changed the value of the number. And I challenge you to take number 1 or number 3. These are 2's complement numbers. And go work out the check system that I've showed you and calculate what this would be in decimal if you were to take these 12 bits, add them all up, and then take just the first 8 bits and add them all up. You'll see that the answer is exactly the same. So try that out as a check to see that when we sign extend a number, we don't actually change the value of the number as long as we follow these particular rules. Next, we're going to talk about what happens when we add 2 numbers that are 2's complement numbers. And there's a couple of cases we have to be aware of where our answer might not make sense and we need to know why. So case 1 is when we're adding 2 positive numbers. If we have 2 positive numbers, we don't have a sign bit, we don't have any negation going on, and we don't really have to worry about our answer being incorrect when we're adding 2 positive numbers. So for example, if I'm adding 9 and 4, 9 would be 1001, 4 would be 0100, and they're both positive. So this first bit here is going to be a 0. When we add all of this up, we're going to see that we get 1101 out as the sum, and we get a carry of 0. And if we think about our answer, this would make sense. 9 plus 4 gives me 13, and this number is 13 in binary. So when you have 2 positive numbers, you don't have to worry about much unless you're adding 2 numbers together where the sum is going to be too big for the space you have to store it. That's called overflow, and we'll go over that a little bit more detail in a second. Let's say that you have case number 2 where you have a positive number and a smaller negative number. So let's say that I'm going to add the numbers positive 9 and negative 4. Remember that negative 4 will be in the 2's complement form. Thus, we're going to represent the number negative 4 using the process that we discussed earlier, and you'll end up with 1110. This is one of the examples we've already done. So if I'm going to add 9 and negative 4, here's what that will look like. 9 plus negative 4. So here's my 9, 1001. Here's my negative 4 right here with my sign bit being negative. This is a 2's complement representation. 2's complement representation. Now, if I were to perform addition like we've shown earlier, we'd go 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 0, carry the 1. So there'd be a carry of 1 right here. 1 plus 0 plus 1 is 0, carry the 1. So if you were to look at this answer, just by doing that addition, if you were to look at this answer, you now need to ask yourself, well, does this make sense? The first thing you should realize is that 9 plus negative 4 is going to be a positive number. It should be positive 5. But if your output from this addition has a 1 in front of it, that automatically means your number is negative because we're in the 2's complement system. If your first bit is negative, that sign bit means you have a negative number that you're trying to represent. So what we do is we disregard the carry if you have a positive number and a smaller negative number, because that carry actually doesn't indicate your actual value. Your actual result, when you add these two together, should be 0101, where your sum is equal to 5. That's not what we're seeing here if we include the final carry in our answer. So what we do is simply throw the carry away. We say we're going to ignore the carry because the rest of the number is right. The rest of the number reflects the right answer, which is what I should get. I'm just going to disregard the carry in this case. So if you have a positive number and you're adding a smaller negative number, the carry, the final carry, is always disregarded. So that's case 2, where we have to disregard the carry. If you have case 3, where you have a positive number and a larger negative number, for example, what if we have negative 9 and positive 4? Well, I know that negative 9 and positive 4 combined should be negative 5. So if I take the number negative 9 and write it in 2's complement form, I'll get 10111. If I take the number 4 and write that in 2's complement form, remember that's a positive number, so you really don't have to convert it. You just have to write it out using 5 bits. This is what I'll get. Now when I add these together, I'll have 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 1 is 0, carry the 1, so there's a 1 right here. 1 plus 0 is 1, and 1 plus 0 is 1. Here's my answer. Now if I go and evaluate that answer, this answer would be negative 16 plus 8 plus 2 plus 1, which is negative 5. And now you have to ask yourself, is that right? Does that make sense? Yes, it does. I started out with negative 9 plus 4. I should be getting negative 5 as my answer. This addition reflects that. So I don't have to do anything special if I have a positive number and a larger negative number. Your carry bit will come out to be 1, or your first leading bit will come out to be 1, but it should be, because if you have a larger negative number, you're always going to have an answer that should be negative. Therefore, your first bit should be 1. Let's talk about case number 4, when you have two negative numbers. Let's say I'm going to add the numbers negative 9 and negative 4. Here's negative 9 in 2's complement form. Here's negative 4 in 2's complement form. If I add these two numbers together, here's what I get as an answer. 110011. Now, if you were to go and calculate this in decimal, you would not get an answer that is equal to negative 9 plus negative 4. Your answer should be negative 13. So we have an extra bit that we're going to disregard once again if you have this case. Two negative numbers, when you add them together in 2's complement form, you're going to get an extra carry that you will disregard. You'll just throw it away. You'll just ignore it. And the result, or your final answer, will be whatever's left. 10011. So that's case number 4. Case number 5, you're going to have equal and opposite numbers. So for example, negative 9 and positive 9. If you have equal and opposite numbers, your answer should always come out to be 0. But if you take negative 9 and put it in 2's complement form, take positive 9 and write that out using the same number of bits, add these two together, you actually get a carry right here of 1, which is not right because your answer should be 0. So you disregard the carry if you're adding equal and opposite numbers, so that your final answer will be 0. So we just talked about addition in the 2's complement system. Subtraction using the 2's complement system actually involves the operation of addition and is really no different from the previous cases we've studied. So what we're going to do is, instead of performing a subtraction problem, we're going to rearrange each expression so that you just will be performing addition. That way we can look at each of the 5 cases we just discussed and determine if there might be a place where you would have to disregard a carry. So we're going to arrange the expression so that we will be performing addition, convert each number to a 2's complement number, perform the addition, evaluate the answer, and decide if a carry bit must be thrown away. And we're also going to see what an overflow error is. Overflow can occur if the answer to be stored requires more bits than what is available. So we're going to watch out for those cases where we have to throw away a carry. We're also going to be looking for cases where an overflow error can occur. So let's look at the first example. We have 12 minus negative 5. So let's first rewrite that as addition. That would be 12 plus 5. Now I'm going to write each of those numbers as a 2's complement number. Since they're both positive, I don't have to convert anything. I just need to write each number in binary, and I need to use 5 bits to do that. 12 in binary would be 01100. 5 in binary would be 00101. So again, I don't have negative numbers. I don't have to convert into anything. I just need to make sure that I use the right number of bits for the number And the last bit is going to be the sign bit, but I know the sign bit is going to be 0 if we have a positive number. That's why I'm going to use 5 bits to write out each number with a 0 coming first. Now I'm going to perform the addition to add these together. If you perform the addition to add these together, you get 10001 as your answer. And again, we're adding everything as a 2's complement number. So a 2's complement number is what you get out. If you were to add this up, 10001 in 2's complement is equal to negative 16 plus 1. Negative 16 plus 1 is negative 15, which is not the 17 we're expecting to get when we add 12 plus 5. This is called an overflow error because the number 17 requires 5 bits before the sign bit can be included. That means we need at least 6 bits to store the number 17. We need 5 bits for the number plus 1 bit for the sign bit. And according to the directions, we only had 4 bits for the number plus 1 bit for the sign bit. So this is what we call an overflow error because the answer we were expecting won't fit in the space allowed. So we won't ever get the right answer when adding these quantities together if we have an overflow error. Let's look at example number 2. We have 12 minus 5. That's our next example. 12 minus 5. So I'm going to write that as an addition problem. I'm going to say 12 plus negative 5. Then I'm going to write out each number as a 2's complement number. So the number 12, that's a positive number, no conversion required other than writing it out in binary. Number 5, negative 5, you are going to use that 2's complement process we discussed, where you write out the value of the number, complement, add 1, add a sign bit. And you'll get this for negative 5 in 2's complement. Again, you may want to pause the video at certain times as I'm going through these examples and do that conversion yourself to make sure you understand where it came from. If not, then you'll want to reach out to me so that we can touch base on the appropriate method to do this. So now that you have converted each number, you've converted the 12 into binary, you've converted the negative 5 into 2's complement binary, now you're going to add these two together. Here's the answer you're going to get when you add this plus this. Notice that we're going to have to throw away the carry bit because we have a positive number plus a smaller negative number. That was case 2 that we discussed earlier. This is one of those cases where you're going to throw away the carry bit because if you include it in your answer, it doesn't make sense. 12 plus negative 5 should be positive 7. This is not equal to positive 7. So we have to throw away the carry bit. Once we do, we can see that our answer is correct. Now we have negative 12 minus negative 5. Let's rewrite this as addition. That would be negative 12 plus 5. Now we're going to write negative 12 as a 2's complement number, and we're also going to write out the number positive 5. Here's negative 12 as a 2's complement number. Here's positive 5. Add those together. Here's what you'll get, 11001. Now you have to ask yourself if that is correct. If I'm adding 12 plus negative 5, I expect to get negative 7. So you're going to need to go evaluate this and see if you actually get negative 7. So you're going to do negative 16 plus 8 plus 1, and you'll see that yes, it is negative 7. So you know your answer is correct, and you don't have to throw any carries away. Next, we have negative 12 minus negative 12. If we rewrite this, you get negative 12 plus 12. Here's the case where these numbers are equal and opposite. So when we add them together in the 2's complement system, we should get 0. So if you take the number 12 and write it as a 2's complement number, here's what you get. If you take the number positive 12 and write that out, here's what you'll get. When you add them together, here's your answer. Is this equal to 0? No, it's not. Here's a case, again, where you have to throw away the last carry because then the final answer is 0, which is correct. Then finally, we have 12 minus negative 12. That would be equal to 12 plus 12. So I'm actually going to just take the number 12, it's positive, and I'm going to add it to a positive 12. Here's the answer we get when we add 12 plus 12. Now think about it like this. 12 plus 12 should be 24. But this right here is equal to negative 16 plus 8, which is negative 8. That's not 24. So we can see that when we add these two numbers together, we do not get what we're expecting. Even if I throw away the carry, I still don't get the answer I was expecting. So that's another overflow error. Because 24 requires 5 bits before the sign bit can be included, and we only have 4. So a great way to determine if you have an overflow error is if you look at your answer, and step 3 here, you look at your answer and you say, well, I know that's not right. Let me throw away the carry. If you throw away the carry and you look at what's left and it's still not right, it's an overflow error. Basically, you just don't have enough space to store the right answer. You need more bits than what was allowed. That's how we're going to perform subtraction in the 2's complement system. And next, we're going to move forward to multiplication. And again, just like with addition and subtraction, multiplication is not much different in binary. It's the same process you've learned in the past. So you're going to write out the two numbers you're going to multiply together, one on top, one on bottom. And then you're simply going to multiply the first number on the bottom by each number on the top, shift over by one column, and repeat. It's the same process that you've learned before. So I'm going to do 1 times 1, then 0, then 0, then 1. That's this first row. Shift over one space to the left, and repeat. 1 times 1, 0, 0, 1. That's the second column here, second row. Next, we have 0 times all of this, so you get 4 zeros. And then 1 times all of this, you have 1, 0, 0, 1. Then you add it all up. Same exact thing as in multiplying numbers in decimal. There is no difference in what you've already learned when multiplying two decimal numbers by hand. It's the exact same process. So on the next page in your notes, I want you to try the next two problems yourself. You're on page 6 of your notes. You have two problems, 1101 times 1001, and 0110 times 1101. So take a second, go back to the 3rd or 4th grade when you learned how to multiply decimal numbers, apply the same process here, and see if you can get the answer. So take a minute to hit pause, try it by yourself, and then come back for the solution. Here's the first one. 1101 is 13. 1001 is 9. 13 times 9 is 117, which is this right here. The next one, you have 6 times 13, which will give you 78, which is this right here. If you weren't able to get those by hand, go back through your work and see if you can figure out the error. If you're still having trouble with it, please contact me so we can go through it together. So we've talked about adding 2's complement numbers and subtracting 2's complement numbers. Now we're going to talk about adding two BCD numbers. Reminder, BCD stands for binary coded decimal. In binary coded decimal, we have a 4-digit code that represents the decimal value of a number. So for example, the number 5 in BCD is 0101. The number 4 in BCD would be 0100. Remember, BCD only covers your decimal digits 0 through 9. 0 through 9. So when we add two numbers that are BCD, we sometimes have to figure out if our answers are going to be correct the same way we have to evaluate them in the 2's complement system. So let's say that we had the number 5 plus 4. Well, 5 plus 4 would be 0101 plus 0100. We add those together, we get the number 9. This is the same process we've used before. As another example, let's say we have the number 45. In BCD, the number 45 would be 4 bits for the number 4, 0100, and then 4 bits for the number 5, 0101. Remember, BCD is different than writing it out in binary. Take each decimal number and write a 4-digit code for that number. The 4 becomes this. The 5 becomes this. Same thing with 33. The 3 becomes 0011. The second 3 also becomes 0011. Now, in decimal, when we add 45 and 33, 5 plus 3 is 8, 4 plus 3 is 7, we expect the number coming out to be 78. When we take two groups of BCD numbers, we may or may not get what we're expecting. In this case, if you take the first number, add it to the second number, 1 plus 1 is 0, carry the 1. 1 plus 1 plus 0 is 0, carry the 1. 1 plus 1 is 0, plus 0 is 0, carry the 1. This would be 1 plus 0 is 1. If you follow the addition, it works out. You get the number you expect in this case. But sometimes you don't. Here's a case where you don't. If you're adding two BCD numbers and your sum is going to be greater than 9, you're going to have an issue. For example, add 6 and 7 together in BCD. The number 6 would be 0110. The number 7 would be 0111. Add them together, and you're supposed to get 13. Now, this is 13 in binary, but it's not 13 in BCD. In BCD, the number 13 would be, the number 13 would be 0, 0, 0, 1 for the number 1, and then 0, 0, 1, 1 for the number 3. In BCD, you got to take each digit and break it down individually. We talked about that in the first lecture of the semester. So when I add two digits in BCD, I don't get a BCD output. So if you have a sum greater than 9, you'll always see that your output doesn't match what you expect. So when this occurs, the sum must be corrected by the addition of 6. The addition of 6. That's what we're going to do to correct this problem. So you're going to take whatever answer you get out, which should be 1101, and just add 6, which is 0110. Add 6 to that answer, and then your answer will look like it should for BCD. So here's that example again. 6 plus 7. Here's our 6. Here's our 7. Add it together, and that's not a BCD value for 13. That's a binary value, but it's not BCD. So add 0110 to your answer, and you'll end up getting a 1 and then a 3, which is your valid code for BCD, the number 13. So anytime you have two numbers you're going to add together in BCD, if they're going to add up to be greater than 9, you have to add 6 to your answer to make it correct. So if you look at your notes, here's another example, 47 plus 35. If I write 47 in BCD, that would be 4 and then 7. 35 would be 3 and then 5. Add those up. We're expecting our answer to be 82. What we get when we add this up is not 8 and then 2. It's not 8 and then 2. So we have to add 6 to correct. Add 6 to correct. If you take this number right here and add 0110 to it, you'll end up with 1000, which is 8, and then 0010, which is 2, which is a correct BCD sum. Your answer should be two groups of 4, where the first group represents 8 and the second represents 2. We didn't get that when we added together, so then we add 6 to that answer so that we will. That will always correct it. Just add 6. Here's a second example where we have 59 plus 38 should be equal to 97. But we get 9 and then 1 here. That's not 97, that's 91. Add 6, and now your answer becomes 97, which is BCD for 97. So we would perform BCD addition. That's the end of the video.